Hi everyone, I'm Katie.
I'm Brittany.
I'm Toby.
And today we're going to be talking about allylic radical halogenation with NBS. And I know what you all are thinking. What is this? Well, guess what, guys? It's only organic chemistry, so just keep calm. Hey Britt, what is this phenomenon we call radical allylic halogenation with that super special guest star NBS?
Well, we will get to NBS a little later, but for now let's start with radical allylic halogenation. When halogens are near unsaturated molecules like alkenes, the expected reaction is addition to the double bond carbons with a product of halogens on adjacent carbons. However, when the halogen concentration is low enough in the reaction, alkenes containing allylic hydrogens instead undergo substitution at the allylic position rather than addition at the double bond. The product required is an allylic halide.
Okay, well, why substitution of allylic hydrogens? Toby?
Well, that brings us to one of our main topics of organic chemistry, resonance. The dissociation energy of an allylic CH bond is lower than the dissociation energy for CH bonds at other positions. This is because the radical formed when the allylic hydrogen is removed and stabilized due to resonance. Since the halogen concentration is low, the allylic position is favored over the vinylic and alkylic positions. Whenever two different resonance structures can be drawn for an allylic radical, two different allylic halides are formed by radical substitution.
Perfect. All right, gang, we're going to walk you through radical chain mechanisms for allylic bromination. Step 1, which we know as initiation, is first. We heat or UV light causes the weak halogen to undergo homolytic cleavage to generate two bromine radicals and starting the chain process. Step 2 of radical chain mechanisms is what we know as propagation. This can occur in multiple steps. The first shown is a bromine radical grabbing a hydrogen to form HBr and an allyl radical. The next part of propagation, which we are calling part B, is when the allyl radical grabs a bromine atom from another molecule of Br2 to form the allyl bromine product and another bromine radical, which can then itself undergo reaction 2A, creating a cycle that can repeat. The third and final step of radical chain mechanism for allylic bromination is what we call termination. Various reactions between the possible pairs of radicals allow for the formation of Br2 or the product allyl bromide. These reactions remove radicals and do not disrupt the cycle. So I know the question on all of your mind. What about NBS? Toby?
Halogenation at an allylic carbon often results in a mixture of products. For example, bromination of 1-butane under radical conditions form a mixture of 3-bromo-1-butane and 1-bromo-2-butane. A mixture is obtained because the reaction proceeds by way of a resonance-stabilized radical. Abstraction of an allylic hydrogen from 1-butane with a bromine radical from NBS forms an allylic radical for which two different Lewis structures can be drawn. NBS can be used as an alternative source of bromine, which is needed to generate the allyl halide.
Alright, so we're going to go over a quick summary of what we learned today. When treated with Br2 or Cl2, radical substitution of allylic CH bonds generates the allyl halide. This process can be compared to alkanes. Reaction proceeds via radical chain mechanism, which involves radical intermediates. The stability of the allylic radical due to resonance favors substitution at the allylic position. NBS can be used as an alternative source of Br2. Thanks for joining us today. This is
Katie.
Brittany
And Toby.
Peace.